in numerical methods, we very often talk about discretization. And discretization is something that I think many people do not understand, that it splits into two completely different things. If we are talking about discretization, then it should mean that we are either talking about discretization of the space, so discretization of the domain where we want to solve our differential problem, and the discretization of equations. These are two things that are distinct from each other. And let's start by discussing the discretization of space. The concept is very simple. If we've got, well, okay, let's give it a title. Discretization of space. The concept is very simple. If we're dealing with just one-dimensional differential problem, then we've got some domain, say the x-axis. Maybe we're interested in solving an equation from the coordinate x equals 0 to x equal 1 to x equal L. And discretization of space needs that we need to divide our domain that contains infinite number of points. We need to divide into finite number of intervals. So we are dividing it into a finite number of intervals. We will have the intervals and we will have some nodes. As you know, no surprise, that we will be referring to something like that as computational mesh, with the mesh nodes. In 1D, we can even just number the nodes with I equals 0 or 1, depending how you want to start, up to I equals n. So we will be having nodes and what you call in between the intervals. This might be elements, this might be volumes, depending on the numerical method, discretization method that we will be using. The same in 2D. No surprise, again, we subdivide the whole domain, let the domain look like that. We subdivide it into a finite number of elements, volumes. We have got the mesh nodes. And that's the concept of the discretization of the geometry or of the domain. Well, quickly remarks. I'm not going to give you a very thorough lecture on, I don't know, on space discretization techniques. I just want to mention a couple of things that I think are worth knowing, and you will be referring to them when writing different codes. Typically, names you can deal with in 2D. We can deal with square or rectangular elements. They are called quadrilaterals. Four-sided might be like that, or triangles. Two most popular ones. Yeah, it is. What's in short? Quadrilaterals. Now it's good. Quads, exactly. Okay. The quad mesh is very difficult to be generated automatically. Like you will find domains like rectangles that are that you can very easily subdivide automatically into quadrilaterals. But generally, there is no general algorithm to divide any geometry into quadrilaterals. When you want to subdivide the space into triangles, there are automatic algorithms that will work always. One of them is the Delano triangulation. Probably at least one lecture on Delano triangulation, but the idea and the concept. What Delano triangulation does, the algorithm takes a set of points. So do not be misled. Delano triangulation does not generate computational mesh. What it does is, given a set of points, it generates triangles such that it's guaranteed that that no point, that if you generate the circumcircles for each of the triangles, there will be no point lying inside of this circumcircle. Okay? Concept like they will be nice.
Why is it so important? Because of the skewness or something like that?
I think it's mainly because of the skewness. So, in a sense, they will be as nice the distribution of points is. Obviously, if you've got very stupid distribution of points, the triangles will not look perfect. But it's guaranteed that they will not. That there will be no point lying within the circumcircle of any of the triangles.
I think like even if the elements will be very skewed, there won't be no points. I think it's more that the triangles are created correctly. So like we've got like those two bottom points and we choose the closest point for them, not for example some other one, and then we would have like the mesh that is
extremely
like
it has intersections.
Yeah, like it has intersection.
Yeah. It's guaranteed that it will work. Delano algorithm can be found in MATLAB if you wish, and you probably already know. It just generates the triangulation P, I think, is the matrix of the coordinates of all the points. Probably, as I would guess, but I'm not sure, probably first point X, first point Y can be in 3D, then nth point X coordinate, nth point Y coordinate, nth point Z coordinate. And this one, what it will return, obviously your points have got some numbers, 1, 2, 3, 4, 5, 6, 7. So this one should return a matrix like 1, 2, 3. We go this way? No, columns represent.
Yeah.
1, 2, 3, then let's say 2, 5. 2, 5, 3, 5, 4, 3. The convention is that you always loop in this direction over over the local nodes. No matter which node you start with, but always this way that you've got your subdomain on the left-hand side when you're circling around it. This one is often called the connectivity matrix. Connectivity always says which points, which nodes you need to connect with each other to form the triangles, volumes, elements, or whatever method you've got. Are there any alternatives in 2D to quadrilaterals or triangles? Yes, there are. One of the concepts, I think polymeshes exploit this concept, but they are not very commonly used. The idea is the following. You can generate mesh by subdividing each of these lines by half. And you create such a volume, or such cells are referred to as Voronoi cells, or if you prefer. And the mesh that is generated by such a procedure, well, obviously you would generate something like that, and something going forward, is called the dual mesh. So if you generate one mesh by the Delano triangulation, then you can move to the dual mesh. Dual mesh is then based on the Voronoi cells. The nice feature is that by definition, when you've got two vertices, then you got the guarantee that the wall that is between these two vertices is very, very nicely perpendicular to the line that connects these two vertices. That's the nice feature, because if we will, when we want to advect any fluxes, convective fluxes, then it's nice to have walls that are perpendicular to the direction of the convection. That's the nice feature. I think from the computational geometry point of view, pretty challenging to handle this mesh. Or maybe not. I don't have experience with polymeshes. And
it's very beneficial to use them in finite volume solvers. And in case of open fold, for example, you start with tetrahedral mesh, then you create dual mesh, and then you can pass it to the solver. So basically, the Delano triangulation, one of the steps of creating such a mesh.
Can be done. One more comment to the Delano triangulation is that it takes as the argument, it takes the set of points, and it always generates a convex triangulation. So it means that maybe natural. Let's say it will not generate something that doesn't have a triangle here. Yeah, it always fills the set of points to a convex triangulation. What's the problem about that? The problem is that if you, for example, generate in your numerical code, you want to mesh the rectangle. Let's do it by hand. Let's say we've got just such a set of points. It would probably work like maybe like that. And now I want to show you one thing, because you would expect having something like that. Not necessarily. Let's remesh it. But note, 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 note. What can happen is the following. Sorry. Nice. Why did it happen? Because you've got some numerical accuracy how you're representing the coordinates of your points. So basically these are, let's say for y equals 1, but maybe this one is 1.00000001. And then it's above. Is it a large problem? Probably not. You can remesh it, you can skip it, or maybe, okay, maybe that's a stupid example, sorry, because I think it would generate something like that, but this point would be higher.
If it's slightly below, this will happen, I think.
Yeah, exactly.
Okay.
But I believe that in case of Delano triangulation MATLAB, you can adjust parameter.
Okay, yeah, that's the proper example. If it's a bit below, and you probably don't want to have such triangles in your mesh. To be honest, if you know that something like that is created, it's pretty easy to come up with the algorithm that, based on the coordinate, will eliminate such triangles or such volumes.
This is currently embedded in Delano triangulation in MATLAB, that you can just
adjust the accuracy, the threshold. Okay, might be, but please do not be surprised if you come up with the mesh that you wanted to have perfectly smooth mesh at one of the walls, and then, well, you open it, it's a mess. It can be a mess, but you can get rid of it. In 3D, quick summary. In 3D, you will have 4 standard types of elements. Very often called bricks. To not play with
I think you use H in between.
That's what I meant.
X, yeah, exactly.
Just call it hex. Hexaedra in plural, in singular, I think hexaedron.
Yeah. That would be
Bricks. Then the other type tetraedron, in plural tetraedra. So generally tetra mesh.
yeah, in Quickersim notion tetras.
Not only at Quickersim, I think most people call it tetra. The other type is, and I don't know if there is any other name, wedge.
Or prismatic.
Yeah, that's right. Or prisms. Prisms, very commonly used notion. Pyramids. What?
Egyptian cell.
Egyptian cell. You might call it an Egyptian cell. I think you need to print a couple of papers in journals with Egyptian cells. Maybe you will create a new trend. Pyramids. Any other names except for Egyptian cells?
It's quite easy, so.
Okay, pyramids. Then quick remarks. In 2D, you can certainly subdivide the whole domain into triangles and nothing else. You don't have automatic algorithms to subdivide into quadrilaterals. I'm not sure if you can generally always subdivide space into quadrilaterals. No?
Take a circle. Have a single triangle.
You can, for a circle, you even generate.
But it's not a structural measure.
Yeah, but quasi, what you do for a circle is you do something like that.
Yeah, but it's not a structural measure.
No, it's not a structural mesh. So you can probably always subdivide into quadrilaterals, but certainly there exists no automatic way of generating structured meshes, because quad meshes you can probably also still generate automatically, but they will not be nice. Exactly. So without going into theory, for practical applications, you will not find good ways of generating quad meshes automatically. Triangular meshes, yes. In 3D, it's important to say always you can subdivide space into tetrahedra. Again, the same problem with bricks. If you generate structured meshes, you can write algorithms for some basic shapes. This will work fine, and it's pretty convenient. Relatively small amount of elements and small amount of nodes, so that's pretty nice. And you can generate the whole space discretization in 3D just based on the tetrahedra. But if you add hexahedra and you want to combine these two types of cells, you absolutely need to add to your code also pyramids and prisms, because there are no ways to always connect hexahedra and tetrahedra with each other. Well, basically because they do not fit to each other. So you need to have something that will interconnect these elements. So just remember, if you're writing code that should handle this and that, you need to handle the additional two types of cells in your code. I see the questions. Just give me a minute. That's it. Okay, questions.
Why does Fluent, for example, in a cylindrical pipe, use by default hexahedron?
That's exactly.
Why would you like to use it?
No, I did it yesterday for a pipe, a cylindrical pipe, and Fluent used it by default hexahedrons.
But
Why?
are you sure you're using the correct word for by default? I mean, it may be the default setting in the graphical user interface.
Anyway, like hexahedra are a very nice type of cells for finite volume method, because generally well-built hexahedra mean that you should be close to 90 degrees angles at the walls. Then if you need to calculate the fluxes through the walls and everything is perpendicular, you've got nice structured meshes if you subdivide the whole space into hexaedra, you end up with the smallest number of finite volumes. So basically the smallest amount of unknowns in your system. If you want to subdivide one brick into tetraedra, just a couple of minutes of focusing on spatial imagination, but believe me, you subdivide it into 6 tetraedra. Sorry?
Konrad was implementing this just a week ago, so...
Okay, so maybe 8. Really?
Even worse.
I think...
You can divide, maybe you can divide in 6, but it's not universal.
Okay, sorry, so maybe 8. But so you already see advantages. Generating bricks for finite volume is nice. You end up with smaller number of unknowns in the system.
You can measure height in such a way that some walls are perpendicular to the flow and others are parallel to the flow, so you have small numerical values.
If you generate triangles and you've got like flow like that into you always have got fluxes that are skewed to the mesh.
But you can always recombine tetras into polyhedrals.
Okay, and the last comment that I wanted to actually said it already. The last comment is that you can always subdivide bricks or any other elements. You can find an automatic way to subdivide them into tetraedra, always. And we do have these procedures in-house. I think it's a hell writing that, because you need to analyze like 32 different variants of how they can be rotated or something like that. Okay, I have seen codes like that, like every combination splits into... Anyway, you can do it. So there exist ways, and we have got these algorithms. So if you would be dealing anyway at any time with such a problem, just go to Konrad and Michał. Okay, what time is it? It's still 15 minutes. That's good. Then we talked about discretization of space. Let's close this topic with discretization of time. There is not much to say after we have described discretization of space. If you've got initial and the boundary value problem, this means that you need to solve something in space and with respect to time. So you probably have x coordinate and time. You've got your space discretization and you got time discretization. Let's say it's t equals 0, t1, t2, and we will be solving for the values of the unknown function for each time step. The same concept, but not for space, but for time, where in this case the mesh is constant across time, does not need to be. You might have moving meshes. One more comment, the time discretization, not necessarily uniform. So I have drawn it like that, but you might have delta T1 and let's say delta T2, which is larger than delta T1 can be. This might be one of the ways to deal with the stiff problems. Maybe you've got some time interval where you need to be stepping with very, very small time step sizes, but then you can increase the time step size because you don't have any huge changes. Then, questions?
Maybe remark.
Yeah.
Even in some methods you can have like non-uniform time step, so you can integrate some cells with larger time step and some with smaller time step. Yeah.
And are there some methods with, for example, the gradient of you do the average of the gradients of velocity in the whole domain, and if it's between this and this.
I have no idea. It was.
I don't know many CFD methods that would be time stepping with variable time steps.
For example, this CFL criteria.
Yeah, okay, could be. I think much more sophisticated methods for choosing the time step size are developed for ordinary differential equations. For example, for the stiff ones where you choose the time step size based on the, for example, the gradient may be on the second derivative, second time derivative, or any other heuristics that you can have.
What about lattice balls non-homogeneous mesh? Different mesh sizes inside the domain. I believe that then you have to variable time step in each cell.
I think you have different time steps than in your smaller and larger cells, but they are constant.
Oh, okay.
I mean, it's like, I think it's called multi-time, no, I don't know. You'd need to check it for a lattice Boltzmann method with changing mesh resolution, that's true. But to be honest, for flow simulations, I don't know many methods or codes that would practically work with variably chosen and variably adjusted time step during the simulation. Well, space discretization and time discretization already covered. So I said at the beginning that there is distinction between discretizing space and discretizing equations. So right now,